When the ground begins to shake, it can change everything in a matter of seconds. The 2011 earthquake in Japan caused over $200 billion in damage. The 2015 Nepal quake left thousands dead and millions homeless. Earthquakes don't just test our buildings, they test our ideas on how to protect them. Today, a new scientific breakthrough is emerging, one that doesn't strengthen buildings from the inside, but instead manipulates the very waves that threaten them. It's called seismic-resistant metamaterials, and while the term may sound complex, the idea is simple. What if we could stop or redirect earthquake energy before it even reaches us? What are metamaterials, really? Let's break it down. Meta means beyond, and that's exactly what metamaterials are. Materials engineered to go beyond the capabilities of natural ones. Instead of depending only on what they're made of, metamaterials rely on how they're structured. They're designed in repeating patterns. Imagine a honeycomb or a lattice that can control waves like sound, light, or vibrations in ways that normal materials cannot. In the case of earthquakes, researchers are focusing on mechanical metamaterials. These are designed to interact specifically with seismic waves, the very vibrations that cause the ground to shake. Imagine dropping a pebble in a pond. The ripples spread outward. But now, imagine placing carefully arranged stones under the water. Those ripples can be disrupted, redirected, or even stopped. That's exactly how seismic metamaterials work. Only they do it underground instead of in water. There are a few clever ways they do this. Periodic structures are patterns built into the ground, like a grid of holes or columns. They create zones called band gaps, which block certain wave frequencies from passing through, similar to noise-canceling headphones, but for seismic vibrations. Resonators are parts within the material that shake in response to incoming waves, but they do so in the opposite direction, essentially canceling the energy out. This sounds strange, but it's a real engineering trick. These materials behave as if they push back against a wave in a way that redirects or absorbs it. One way to picture this is like stepping on a trampoline that pushes you back less when you step harder. It reacts opposite to what you'd expect. By placing these specially designed materials underground or around buildings, engineers can deflect, absorb, or weaken the seismic waves before they ever reach structures. If you're new to my channel, please check out my videos and consider subscribing for more content like this. Thank you for your likes, shares, and subscriptions. This isn't just theory. Across the globe, researchers are testing seismic metamaterials in real conditions, and the results are encouraging. In France, engineers have drilled grids of vertical boreholes into the ground to study how they interact with seismic waves. These structures, buried like a hidden fence, were shown to reduce the energy of waves passing through them, an early but important demonstration of how metamaterials could work at scale. China is also making strides, installing underground arrays built from concrete and polymer components to redirect ground vibrations. These systems are being explored as a way to shield critical infrastructure, particularly in earthquake-prone zones. In Japan, a country with decades of seismic experience, scientists are developing advanced building foundations layered with metamaterials. These are designed to reflect or absorb seismic energy before it reaches the structure, enhancing existing earthquake-resilient architecture. Researchers in India are contributing as well, particularly in the Himalayan region, where the risk of earthquakes and rockfalls is high. They are exploring how metamaterials can be adapted to varied soil conditions and rugged terrain, working toward solutions that could offer protection in areas with both seismic and geological hazards. Beyond earthquakes, there is also interest in using these materials for rockfall mitigation. In parts of Europe and Asia, pilot projects are investigating how structured barriers can scatter or absorb the energy from falling rocks, offering a potentially more efficient alternative to conventional barriers. All of these efforts, whether in labs, on test sites, or in the field, are helping to move seismic metamaterials from concept to application. Of course, no breakthrough comes without challenges. One major issue is scaling up. Most success so far has been in small-scale tests. Translating those designs into large, real-world systems that protect entire buildings or even city blocks is a major engineering challenge. Cost is another factor. Building these underground structures is not cheap. It often involves digging, drilling, and placing precisely engineered components deep in the soil, all of which require time, labor, and funding. Then there's the unpredictable nature of earthquakes themselves. Not all quakes are the same. They vary in strength, frequency, and direction. This means one metamaterial design might work brilliantly in one area but perform poorly in another. Researchers are now exploring adaptive designs, systems that can be tuned or adjusted depending on the type of waves they need to handle. Despite these hurdles, progress is being made, and interest from governments, universities, and private companies is growing worldwide. Seismic metamaterials aren't science fiction. They're science in motion. They're giving engineers and scientists a brand new way to tackle an age-old problem. And while the journey from lab to city is still underway, the foundation, quite literally, is being laid. Because sometimes the best way to protect what's above ground is by rethinking what lies beneath it. Thank you for watching this video. I'll catch up with you in another exciting video soon. Until then, goodbye and take care.